Welcome to my channel. In the previous video, I explained method time complexity. Now, in this video, I am going to explain quick sort. So, that name itself shows quick sort means it is quickly sorting the given elements in the array by comparing the elements from left side and right side. Whenever sequence is not in order, it automatically interchanges those elements in this quick sort procedure. But actually, what was happened in the merge sort is so method generally divides problem into two equal number of elements. Means it divides the problem into two subproblem segment, but that is not happening in quicksort. So based on nature of the elements, quicksort partitions the array elements into either best case, worst case, or average case. So that's why we get three different time complexes under quicksort. But in merge sort, worst case, best case, and average case time complexity is same. That is order of n log n, because that was the very rigid or straightforward approach. Any array, if you take or if you give any array as input to merge sort, which blindly divides that particular array into two parts at mid. But here that is not going to happen. But that too, of course, at mid also that may be happen, but that is based on nature of the elements. Okay. Now, first I will write what is quicksort procedure. Because this quicksort is using a partition as a separate procedure for dividing array elements into two parts. Okay, that particular division may happen best case way or worst case way or average case way, but that particular division depends on the nature of the elements. Now I'm going to write the quicksort, one particular subproblem sorting procedure. Okay, suppose algorithm quicksort of you can take any subproblem like initial index number is p and last index number is q in the subproblem. Then what is actually the divide and conquer approach? Divide and conquer approach is initially verifies whether problem is smaller or larger. But in quicksort, the beauty of the quicksort is if problem is smaller, we say that that particular element is there in a solution sequence. So we need to verify first. If p is less than q, what do you mean by p is less than q? P is low index number, q is high index number, then this is larger. Then problem is relatively larger. So in this case, for partitioning the array into parts, which uses quicksort is using partition as a separate procedure. Partition as a separate procedure, and which takes array name as element, array name as first parameter, p is second parameter, q plus 1 is third parameter. Why q plus 1 I will tell you. Okay, in partition directly which are initializes two parameters. One parameter is used for selecting the greater elements at left side part, and another parameter or variable is used for selecting smaller elements than the first element in the right side part. So both are initialized at one particular location. They are directly incremented and decremented. So first parameter which is started at left side part is directly incremented by 1 unit, and right side variable is directly decremented by 1 unit. Suppose if you start right side variable at last element, after decrementing only we are comparing against the selected element, because here we are using one key element or pivot element for a comparison. I initially starts at pivot element in the partitioning procedure, and J initially starts at outside of boundary. Suppose if number of elements are n and array index numbers are 1 to n, then second variable should start at n plus 1, because in partitioning procedure directly J will be decremented by 1 unit. At the decrementation location, the element is compared with the first element or key element. If you start J at last question means Q, always we lose Q from the comparison. That's why we are supposed to start second variable which is used for selecting smaller elements at right side part at outside of the array. If number of elements are n and index numbers are 1 to n, start j at n plus 1. That's why we are incrementing high index number at q plus 1. Then directly we can start j here and high here in partition procedure. I will explain. Okay na? Generally this partition procedure ultimate aim is finding partitioning location, because if you apply this partition procedure on any example, I will tell you by taking one example, I will explain partitioning procedure. If you apply partitioning procedure, the aim of partitioning procedure is bringing all the smaller values which are there at right side part into left side part, and pushing all the greater values which are there at left side part into right side part. So while making this particular pushing and bringing the values, okay, so those two pointers may be crossing each other, because I have already told we are using I for selecting or fixing greater values at left side part, and we are using J for any other variable. You can name your own way. Okay, J for fixing smaller elements at right side part, and we are Comparing location numbers of I and j. If I is less than j means still greater values are there at left side path. Then immediately interchange is required. That is quick. What that name itself quick. Okay. So whenever after fixing I and j location numbers, one is at left side path, another one is at right side path. If I is less than j, so we can say that generally I is used for fixing greater elements. J is used for fixing smaller elements. If I is less than j means still greater elements are there at left side path of array and smaller elements are there at right side path of array. Immediately perform interchange between these two elements, not index numbers. The values which are there at I and j, immediately perform interchange. And if you repeat this particular procedure, after some time, the I crosses j. This is called as crossover. So once I and j cross each other, immediately interchange. Now we are not going to interchange a of I and a of j. Now interchange the first element, whatever the element you selected as key element or pivot element, then interchange that key element with j. Then the beauty of the interchange is, once after interchanging key element with j element, now key element occupies jth location, jth element occupies first location. Is it clear now? Now if I observe the elements which are left side of this particular jth position element, means partitioning location. We call it as partitioning location. All the elements which are there at the left side part of j or smaller or equal to j, and which are the elements which are greater right side of j are partition location, which are greater than or equal to partitioning location. Then we treat it as partitioning location. Then select left side part as one problem and right side part as another problem. Okay. So from this partitioning procedure, we get partitioning location. Assume that partitioning location is either any name, suppose j. Then take other names here. I will tell you in partitioning procedure. So partitioning aim is partitioning the elements into partitioning the array into two parts. But here, while partitioning, the partition beauty of this partitioning is which brings the smaller elements from the right side part into left side part, which pushes greater elements in the left side part into left side. If greater elements are there, this procedure pushes those greater elements to right side part. If right side part is containing smaller elements than the key element or pivot element, generally we select randomly we can select key element or pivot element in partitioning. But we select the first element, that is the default element. First element will be the key element. Always we compare ith location element with key, jth location element with key, and we are fixing ith location if a of I is greater than key element, and we always fix the jth location if a of j is smaller than key element. After fixing I and j, we are based on I and j relationship. If I is less than j, we conclude that still greater elements are there at left side part, because we are using I for fixing greater elements and we are using j for fixing smaller elements than the first element or key element. If I is less than j, then immediately interchange a of and a of j. This interchange procedure brings smaller elements to left side portion of the array and pushes greater elements to right side part of the array. Okay, na? So if like incrementing and incrementing I and decrementing j and fixing, in this scenario, after some time I crosses j. In that case, immediately interchange key element, means first element with the jth position element. Now that package, after interchanging, that jth position element acts as a partitioning element, and that location is treated as a partitioning location, and we are treating it as j now. That partitioning location is j. This is the resultant of partitioning procedure. Okay, now this entire array is divided into two parts. One part is containing the elements which are less than or equal to partitioning element, and another part, right side part, is containing some elements which are greater than or equal to partitioning element. Then we say that here we can conclude that a of j is in its original location. Then we need not consider a of j. Now consider left part and right part of j and apply quicksort. Immediately call quicksort on two problems now. One is P2 j minus 1, because a of j is there in its own location, that is sorted, and another quicksort is applied on right side part of j. Right side part of j is j plus 1 to right side I index number is q. Okay, na? So this is the simple quicksort procedure. So quicksort procedure immediately verifying index numbers. If index numbers relationship is this, immediately which calls partitioning procedure. Partitioning procedure partitions the entire array into two parts at partitioning location, and that partitioning location is partitioning the array into two parts. And left side part we need to call quicksort independently, and right side part also we need to call quicksort. Again quicksort starts here. Is it clear now? Now I am going to take one example and I will explain how partitioning takes place on that particular example now. Now I am going to explain partitioning procedure by taking one example. In Visual Quicksort, I called the partitioning procedure at initial index number and final index number plus 1. Then I can directly start I at initial index number element and j at final index number plus 1, because anyway we need not mention final index number plus 1 element. Only up to P to Q are the original array elements. But initially we are taking j at q plus 1. But anyway in procedure we are incrementing I by 1 unit directly and j by 1 unit directly. Is it clear now? Okay na? So first assume the key element. Key element is 65. Initially we are assuming first any randomly we can select any element as key element, but here we assume key element is 65 and start I value at also take index numbers. There are 9 values. Okay na? Initially start I value here. Start I value at first index number and j value outside of the problem means 10th location. At 10th location start j value, but we not mention 10th. Just physically we are assuming that this 10th location element is plus infinity, but we not mention plus infinity in the problem. Okay, so start j value at outside of the boundary and start I value at first location. Okay na? Then increment I by 1 unit. Now key is 65, increment I by 1 unit. And immediately verify after incrementing I by 1 unit at the new location of I, whatever the value that is there in the array, immediately compare that element with the key element. What is key element or pivot element? We call it as pivot element or key element. Now, if that particular ith location element is greater than key element, then fix I value here. Fix I value here. Then decrement j by 1 unit. Then from outside of the boundary, now j reaches first element, means last element in the array. Suppose if you start j here, but our procedure automatically decrements j by 1 unit. After decrementing j only, we are comparing jth element with the key element. That's why if you start j directly here, we always lose last element. Okay na? For avoiding that situation, we are supposed to start j at last index number plus 1. Whenever you decrement j by 1 unit, it automatically comes to last element. Okay. Now compare A of j. A of j is 45 with 65 because key element is 65. If it is smaller than key element, then fix here. Okay na? So I is, what is I value? I equal to 2 means index numbers. J equal to 9. If the relationship between I and j is less than, if I is less than j, I have already explained, means still greater elements are there at left side path and smaller elements are there at right side path. Immediately perform interchange. If I is less than j, interchange A of I and A of j. Okay na? After interchanging A of I and A of j, what is the updated array now? 65. 45 comes to 70th place, means second index. 75, 80, 85, 60, 55, 50 and 70 occupies here. So earlier j value is there here, earlier I value is there here. Okay, same procedure. Again, until crossover occurs between I and j, we are supposed to repeat the same procedure. Again, increment I by 1 unit and verify whether A of I is greater than a key element or not. Key is fixed now. For the first cycle, key is fixed. Okay na? For first cycle, key is fixed, that too for the first element in the original problem. Okay na? Now fix I here because A of I is greater than 60. That is the first greater element from left side path. Then fix I here. Then earlier j value is there here. Decrement j by 1 unit and verify at each and every new location of j and a new location of I. We are supposed to compare A of I with the key element and A of j with the key element. We are supposed to fix I value if A of I is greater than key element. You are supposed to fix j value if A of j is smaller than key element. Now fix j here. This is the first smallest element from right side path. This is the first greater element from left side path. Okay na? So after fixing I and j, what is I? 3. I equal to 3. What is j value? J is 8. Still I is less than j. What I told? If I is less than j, immediately interchange A of I and A of j. Then perform interchange between these two elements. Then updated array is 65, 45, 50, 80, 85, 60, 55, 75, 70. Okay? So earlier j value is here and earlier I value is there here. Okay? Again, same. Increment I by 1 unit. After incrementing I to this location, immediately compare these two elements. Key element with A of I. Now A of I is first greater element from the left side path. Then fix I here. then decrement j by 1 unit. Earlier j value is there here, decrement j by 1 unit. Now this is the first smaller element from right side path. Then fix j here. What is I value? I is 4. What is j value? J is 7. J is 7, I is 4. Okay, then I less than j here. So if I is less than j, what I told, if I is less than j, general I is used for fixing greater elements and j is used for fixing smaller elements than key elements. Still, greater elements are there at left side portion of the array. Then immediately perform interchange. Immediately perform interchange. Then interchange these two values. After interchanging, we get 65, 45, 50, 55, 85, 60, 60, and here we get 80, 75, 70. Okay, 75, 70. Where is ith location? Earlier ith location? Earlier ith location was this. Earlier jth location. Where is earlier jth location? Earlier jth location was this. Okay, earlier ith location was 4 and earlier jth location was 7. Okay, again here still I is there at left side portion of the array, j is there at right side portion of the array. Then increment I by 1 unit. And again immediately compare. After reaching new location by I and j, immediately compare a of I and a of j against key element. A of I is 85. This is first greater element from left side. Then decrement j by 1 unit. This is first smaller element from than the key element. What is I? I equal to 5, j equal to 6. I equal to 5, j equal to 6. Then a of I is I less than j now. If I is less than j, then immediately interchange a of I and a of j. Now perform interchange between a of I and a of j. Now I am going to rewrite the array, resultant array. After that, I will explain what will happen if you increment I and if you decrement j. After interchanging a of I and a of j, we get 60 to ith location and 85 to jth location. Okay, na? Again, still I is there at left side portion of the array and j is there at right side portion of the array. Again, increment I by 1 unit. If you increment I by 1 unit, I reaches here. What is I value now? I value 6. And decrement j, because this is first greater element than key element. Then decrement j by 1 unit. Then j comes to fifth location. Now this is first small element from the right side path. What is I value? I is 6, j equal to 5. But for all the earlier cases, I was smaller and j was greater. But now I reaches 6 and j reaches 5 just by using this particular I and j relationship, because I is greater than j now. Once I is greater than j, we conclude that all the greater values, just by using partitioning procedure, all the greater values are already pushed into right side path, and all the smaller values have already transferred to left side path, already brought into left side path. Is it clear now? So once I is greater than j, what is the key element? Key element is 65. Key is 65. Then here we are supposed to interchange key with a of j. Interchange key with a of j. Now what is a of j? 60. Because jth location is 5. At fifth location, the element is 1, 2, 3, 4, 5. At fifth location, element is 60. What is key element? 65. So once crossover occurred between I and j, once I is greater than j, simply also here also we are interchanging. Here also we are interchanging, but we are not interchanging a of I with a of j. Here we are interchanging a of j with key. A of j with key element. Once you interchange a of j with key element, then what is the updated array now? Updated array is now 60 comes to 65th location, means first location, and 65 comes to 5th index number. Then if you rewrite it, 60 comes to here, 60, 45, 50, 55, 65, 85, 80, 75, 70. Now we treat it as a first pass. We treat it as first pass because this is jth location, this is jth location, this is ith location, earlier ith location. Now we interchange because I crossed j now. I crossed j, that's why we interchange key element with a of j. This is we performed. That means we are interchanged 65 with 60. Then 65 comes to jth location and 60 comes to this location. Now, if we observe, now we treat it as a first pass. If we observe jth location element with all the left side elements and jth location element with all the right side elements. What is the nature of left side elements compared to jth location element now? After interchanging, that too, after crossover occur between I and j, we simply interchange the key element with the jth location element. After interchanging, if we observe the elements left side part of this 65 and right side part of the 65, all the left side elements are less than or equal to 65 and all the right side elements are greater than or equal to 65. Now, this is about partitioning procedure. Then the partitioning procedure returns J as a result now. What is J? 5 is the result. In quicksort procedure, I have already written J equal to partition of array A, P, Q plus 1. Is it clear now? At Q plus 1 we started J, at P we started I in this. Okay. Now this procedure ultimate goal is returning partitioning location. Now what is partitioning location? 5. But we are treating this is one problem, this is another problem. Why? This is already there in this particular location. This is 5th greatest number in the array. Yes or no? Because all the left side elements are greater than this. All the right side elements, all the left side elements are smaller than this. And all the right side elements are greater than this. Then we say that 65 is sitting in its original location. Then our target is sort left side part and right side part independently. That's why in quicksort procedure, we called we called the quicksort on 2 problems. One is on this, another one is on this. What is the location numbers here? 1 to 4 is one sub problem. 5 we are not considering because 5 is sitting in its original location. It is already sorted. And 6 to 9 is another problem. Again we call a quicksort on this problem and quicksort on this problem in quicksort procedure. Again, if we call quicksort on this, again which immediately calls partitioning procedure if I is less than j. Our initial location number is less than final location number. Immediately we call partitioning procedure. Okay, so this is the beauty of partitioning. There is no ladder merge required. There is no need of applying merge here because this partitioning location always once partitioning procedure is over, whatever the partitioning location, that partitioning location element is there in its own location or original location, then we need to sort this problem and sort this problem separately by using this procedure. Again quicksort, apply quicksort on this, apply quicksort on this, and once you apply quicksort, which immediately calls partitioning on this, if you apply quicksort on this, which immediately calls partitioning on this, the same way, whatever the way we used in first pass, apply in second pass, apply quicksort on this and quicksort on this, which immediately calls partitioning on this procedure, partitioning on this procedure. In that partitioning, take 60 as key element. I is started here. J is supposed to be started at 5th location because 1, 2, 3, 4 only up to 4th location. This is high and J starts at 5th location means Q plus 1 in the original procedure. Then J will be decremented by 1 unit and I will be incremented by 1 unit and I and J are fixed based on the previous explanation. And once I, J cross each other, we are going to interchange key element with the jth location element. Again that jth location element is acting as partitioning element and again we need to consider left side part of partitioning element as one problem and right side part of partitioning element as another problem. Like that we apply all quicksort on all the sub problems and finally we get sorted array without applying merge sort. But the drawback in merge is in merge we blindly divide the problem into sub problems at mid. There we need to apply merge. Later merge means finally we need to combine all individual problem solutions. But here need not combine solutions because once procedure is over, we get the entire array in sorted order because in first call this is sorted automatically. In second call one of the number will be sorted here. In one of the number will be sorted here. And then based on that we select left side and right side part of this and left side and right side part of this. If you go on apply quicksort on left sub problem, right sub problem, again we get another 2 problems from this, another 2 sub problems from this. But those are automatically, whatever the partitioning elements, those are selected in left side part and right side part. Those are sitting in its original order. Okay. So now I am going to write what is the partitioning procedure. Okay. Already explained now. The same explanation is there in partitioning procedure. Now I am going to write the partitioning procedure and I will explain. Okay. So this is the partitioning procedure. Here M is holding P in the previous problem and P is holding Q plus 1. Because in partition procedure we called partition on A comma P comma Q plus 1. Q is final index number of the sub problem and P is the initial index number of the sub problem. Anyway, we incremented already. We incremented Q to Q plus 1 Means we initially started P at outside of boundary because A is copied into A, P is copied into M, and Q plus 1 is copied into P. Then directly we can start J value at P. Okay. So initially assume first element will be the key element or pivot element, and start I value at M means initial index number, and start J value at outside boundary means final index number plus 1. Anyway, Q plus 1 is there. We directly copy Q plus 1 into P now. Okay. So we need to repeat the original procedure until crossover occur between I and J. We need to repeat this entire procedure until crossover occur between I and J, means I greater than or equal to J. If I is greater than J, immediately stop the procedure and make this particular swapping and return J value. This is partitioning location. Then what is going to be happened internally in this procedure? So I have already explained increment I by 1 unit. Initially I is started at first location, then increment I by 1 unit and compare this. If A of I is greater than B or not, we need to verify. Otherwise, repeat the same procedure. Increment I by 1 unit until we get this situation. That is first greater element from the left side part. Once you identify A of I is greater element than key element, fix I here. Fix I. Then at the same moment, decrement J by 1 unit until A of I less than or equal to B. Means by using this, we are selecting first greater element from the left side part than key element. And by using this decrementation, we can select first smaller element from the right side part than the key element. Once we fix I and J, here by using this we can fix J. Once after fixing I and J, we are immediately performing comparison between I and J. Index numbers. Here we are comparing index numbers. If I is less than J, what I told earlier, if I is less than J means still greater elements are there at left side part of the array and smaller elements are there at right side part of the array. Immediately perform interchange between I and J. Then interchange A of I and A of J. Again, here we are immediately calling interchange function. We know interchange function. How can we interchange? Generally, interchange of I comma J. How interchange is taking place? So assume another temporary variable, suppose X. Assume another temporary variable X and copy one of the value into X and copy second value into first value. Okay, na? And copy X into second item. So like this, just by using one temporary variable, we hold first element or second element in temporary variable. If you hold first element into temporary variable, we can call second element into first element location because first element is already safely there in X. Then finally we can copy X into A of J. So this is interchange. Okay, na? So like this we can interchange by taking one temporary variable or third variable. Okay, na? But this procedure must be repeated until crossover occur between I and J. Until that, we need to increment I and fixing greater value and with incrementing J and fixing smaller value than the key element and comparing index numbers. If I is less than J, we are performing interchange between A of I and A of J like this. This particular procedure will be repeated until crossover occur between I and J. Once crossover occur between I and J, this will be this particular condition becomes false. Then what we are going to do? Simply whatever the jth location element, copy that jth location element into mth location. Anyway, we already safely placed in V. No need to worry about whether, because after copying A of J into A of M will be overwritten or replaced with A of J. But safely we place the V, A of M in V. Then directly we can copy A of B into A of J. This is clear now. So whatever the J, once crossover occur between I and J, whatever the element that is there at jth location, simply copy jth location element into mth location. What is mth location? First location in the array. Okay, na? Then that location will be overwritten by A of J. But safe side, we place A of M in V. Simply copy V into A of J. Once this particular procedure is happened on given array, okay, we say that from the jth location element we have already observed in previous example. From the jth location, if we observe the element, all the elements from the jth left side part of jth location are less than or equal to jth location element, and all the right side part elements are greater than or equal to jth location element. Now, this jth location element, jth location is acting as partitioning location. Then this particular jth location element partitions the array into two parts. What was the original one? P to Q. Now J is somewhere here. Okay, na? Then we are not considering jth location. P to J minus 1 we are considering. P to J minus 1 we are considering. And J plus 1 to Q we are considering. This is now becoming one array. This one is becoming one array. Again we are applying quicksort on this. Again we are applying quicksort on this. Okay, so we are applying quicksort on first subproblem, we are applying quicksort on second subproblem, and we go on applying this until getting the sorted order list. So this is about partitioning procedure. This is about partitioning procedure. Like this, by using partitioning procedure, we can sort the elements, but there is no lot or much required because automatically once one pass is over, we get one particular element at its own location. Once you apply second pass, in second pass we are applying quicksort on two subproblems. In second pass we get one element here in sorted order, one element here in sorted order. So like that, if you go on applying partition procedure, quicksort on selected subproblems, internally which uses partition procedure, and it partitions the array into two parts like this. And finally once quicksort is over means we get the sorted order list. Okay, so in the next class I'm going to explain quicksort time complexity. Now, unlike merge sort, we cannot get the same time complexity at best case, worst case, and average case because we don't know. Based on nature of the elements, the partitioning procedure is going to partition the array into the best case, worst case, or average case. So, in the next class, I am going to explain. In the next video, I am going to explain the time complexity of quicksort. Thank you for watching my video. Thank you.